Hi, welcome to a new Cube video. Did you notice the difference? In this video I demonstrate you CubeGUI plugins which allow you to study performance of iterations in loop of your code. Let's do it. Hello and welcome to a new Cube video. We are back into our terminal, and in this video I demonstrate you one plugin, Heatmap, which allows you to study performance behavior of so-called iterations, so loops. If you want, typically if one instruments the source code, the loops and every performance within a loop is aggregated, and one doesn't resolve the individual iterations. Like, for example, from 0 to 10, and there are any calls happening in every iterations, one will obtain aggregated call tree. But if one has a situation that iteration 1 behaves significantly different than all others, it's like initialization iteration or anyhow, and one has to study the performance of individual iterations, one has to resolve these iterations in a profile and make the individual measurements for every iteration. So, of course, I will not explain you how to do such measurement, but at least I can show you where to find information how to make such measurement. So we go over internet, score P, we go into the website virtual HPC, and here down we have score P documentation. Oops. And we go HTML, and here we go to related pages and application instrumentation. So of course here details. What is interesting for us is manual region instrumentation, so we go here directly here, and then we can see that we can mark our regions, and such region can be body of a loop, and we have to mark this loop as a region type loop or dynamic, and we have to then it will be done instrumented individually, and this type of measurement is then described in the dynamic region profiling. So we click here, and here is described actually what's happening, and which profile is then created, and usually it leads to large cube files. So in order to save space, because the iterations are similar to each other, so one can cluster them, and for that one would enable clustering, and then the cube file would have then individual iterations. So I will not explain you how such clustered cube looks like. This I will demonstrate in another Cube video about internals of Cube, and where I will explain exactly this clustering algorithm and how it is encoded in our metadata description. So just subscribe and don't miss it. And here in this document you can read how you can measure individual iterations of a loop. So, assuming you have done it, you would like to actually analyze such profile. So how such profile looks like. So before we move on, I remind you to subscribe, press like and comment if you have any questions. Hopefully so far not yet. Here we start our cube file, CubeGUI, and we open an example of profile, which is a typical BTMZ profile result of the measurement. So if we, that is the profile, so we have here typical standard score P matrix, and here is our call tree. We see that we have 280 elements, so 2 nodes, 8 and 8 ranks. Each of them, so it is hybrid execution, so five OMP threads. So, and we have there are additional plugins, and the plugin which is interesting for us is Heatmap. And so far here is no data to display because Heatmap displays exactly this iteration. So we have selected here top of the call tree. There are no iterations on this level, so Heatmap doesn't show anything. And then if we expand it, and we see here is our loop, and if we expand it, we see that we have here iteration from 0, first iteration, up to 200s. So we have the loop with 200 iterations, and we have the timing. So first iteration was 10 seconds, I mean aggregated, of course. If we take a look at, so it is actually 0.113. Another is a little bit less. So there is a distribution in timings, of course. And if you open the iteration, we see that there is a call tree. So there is a exchange QBC call, and there is ADI. In another one was exchange QBC and ADI. And we see also difference in execution times. Of course, one can study step by step, iteration by iteration, what's going on. But of course, one will not see global picture how the iterations behave. So exactly for this goal, we have this Heatmap plugin. So if we have such a loop or such a call path, call C node where the loop is marked, then we can use this Heatmap. If we click on it, we still have no data to display. Why? Because the iterations are resolved. In order to display something, we have to aggregate these iterations, and for that we actually have to go on this C node, and we see here into context menu hide iterations. So if we click hide iterations, we see that on the next level iterations are hidden. So the call tree is actually aggregated. It is displayed aggregated. Actually, behind the scene, the iterations are resolved, and it is marked here 200 iterations. And here we immediately see this data, and we see on a vertical axis, these are our locations. So from 0 to 5, so first threads, and then another MPI, there another MPI, another MPI, and up to the here. And in the X horizontal, we see actually our iterations. So if we click here, we see that the coloring is changing. So like for example, if we select this exchange QBC, we see that we have very little value, it's blue, on every OMP rank, and significantly higher value on corresponding master threads. Yeah, so if we go on this point and press right click, we can save the image, but left click, we see that thread 45 iteration 22 is value so and so, and in this way we can navigate through individual values, and we see that between the master thread, which is 0.01, and corresponding OpenMP threads, like 100 times order of magnitude difference for exchange QBC. And if we click on ADI, we see that here is the runtime on master threads and OpenMP threads is nearly the same. Coloring is for coloring, the plugin is using this color map. If we just go for display and we can select, for example, advanced color map, and we see that with this coloring, the coloring of this Heatmap has changed. We can select, of course, for example, another coloring, this, and in this way we can highlight maxima, so either minimal or maximal value, and the averages would be then white, and so on. So let's go to default, and that is in principle that's it for Heatmap. So if we explore the call tree, we can actually go down up to the individual the OpenMP loops, for example, and we see that here is the master thread makes majority of work, and the workers are having the less work. So in this particular loop, it is underload. If we collapse them, then together with this implicit barrier, where obviously the worker threads, they have to wait till master is done. So here is a opposite picture, but together it's more balanced picture, but one has to keep that the OpenMP parallel has a barrier. We can see that during the runtime there is variation in execution time. Like for example here the value is really high from whatever reason, maybe some initialization. We see that the upper part, the thread 40, this thread and this thread, they have really low value, and this one have a higher value. This difference in, of course, is second digit, so it is maybe only artifact of mapping of values between min and max. So one has to study then in details whether this difference between this and this value is indeed so relevant or not. But if one goes into the individual loops, then one can see the workload is really imbalanced between master thread and the worker threads, and then one can of course take a look where is actually the difference. So here is obviously master threads is very involved. Here is the master threads is doing a lot of job. And this particular OpenMP structure is a little bit different. On this MPI rank structure is a little bit different, and so on. So this Heatmap allows you to study behavior of loops in more detail than just clicking in a call tree where one doesn't have good overview. As I mentioned, right click would save you this picture, and if you go into plugins and system Heatmap, so there are settings, so if you click on it, then you can see that you can control where the ticks are displayed. For example, here it was really one setting, here specific number of major ticks, let's see, number of minor ticks, and that changes of course this display, so you can control quality of your picture how you want, but actually that's it. There is to find out whether you have iterations, for that you have to go actually on doesn't matter on which call tree, just go on info, and if you go on this global information, this is information about the cube as a total. So one can see here additional attributes, and these attributes, that is actually the part of this clustering algorithm. So we see here 200 iterations, and we see of course C node ID where the loop is actually detected. So that will show you that the loop has been instrumented using clustering. One could actually have the loop without this clustering. There would be every individual iteration resolved. Then you would have to mark loop manually. One can have also measurement of a loop without enabled clustering. Then one would have no information about any loop as a specific attribute, and therefore plugins, Heatmap and others will not be enabled because CubeGUI doesn't recognize whether it is some loop has been measured or not. However, there is a solution for that. So for that we have to open another cube. We go here, and that is, I guess, this one. So if we take a look at this measurement, that's some application, and we open it here, we see that here is some loop is instrumented, and every iteration is called instance. It's just how one instrumented the source code, and there is a body of the loop is then recorded as a subtree. In a structure, this call tree is a loop with a resolved iteration. So theoretically, we could use the very same analysis, and we actually can do that. For that, one has to select this body of the loop itself and right-click in context menu, and there is a point set as loop. So if we click it, the CubeGUI marks it as a loop, and one can see that it enables also heatmap and bar plot, but however there are no data, there is no data yet to display. If one expands it, there are still all iterations are resolved one by one. And here we can proceed as I just showed an example. One can go in the context menu and press hide iterations. Then this level where every iteration, instance 1, instance 2, is interpreted as a different iteration of a loop, and it will be merged, and then one gets usual display of a heat map. So if one selects, for example, here metric time, and one can see that here is some values are really high, the others are low, and then we can study actually this instrumented loop as I just explained. And if we take a look at the info, we see that here are no clustering whatsoever is enabled. So therefore we have to manually mark this loop having iterations. Theoretically, it could work with any subtree. Just next level of children is then interpreted as iterations, and they can have arbitrary names. It's just the fact that they are children, they are basically interpreted as iterations, and they will be then merged. So how many direct children are in that corresponding call path, so many iterations. The corresponding the call tree, they might be absolutely incompatible, so merging would result in just a big subtree, and analysis might be actually misleading. But if you have a situation that you have actually kind of iterations like structure, so maybe multiple calls of some function or something similar, and then you can interpret it as the iterations of a loop, then you can manually mark it as a loop and do this very same analysis. Okay, but anyway, this is a simple plugin which allows you to study behavior of iterations of your loops, and hopefully that helps you in your future performance analysis. And again, if you like this video, please subscribe, press a like, put in comments any questions, and see you next time.